Hi, Damien. Thanks for taking the time to come on board and talk to me about MicroPython. How are you doing today?
Hi, Kwabena. Yeah, good, thanks. I'm pretty good. Yeah, it's pretty exciting times with microcontrollers and all things that have been going on, new developments.
Yeah, yeah. So, it's it's really bright out there, right? Like, where are you at right now?
uh, in Australia, and it's like midday and it's midsummer, so it's pretty hot today.
It's pretty hot and sweaty. Oh, okay, that's nice though. It's not the winter, I guess, then, because you guys are down under, right?
That's right, it's the opposite. We are backwards.
Yeah, in San Francisco right now, it is cold and stormy. Been raining quite a bit, actually.
Yeah,
Um, yeah, but yeah, today, I just wanted to talk to you about tell me about MicroPython. Tell me about how it got started. You were in Cambridge at the time when you created it. How did you think of this, and how has it been growing over the last? I mean, it's been over a decade now. Like, I want to
yeah,
hear about your journey and MicroPython.
yeah. Well, it was sort of at this time when Kickstarter was a new thing. Well, been going on for a few years and had quite a lot of momentum, lots of interesting original projects on Kickstarter. And that was sort of the thing that caught my attention. I also had the idea for a long time of trying to get a scripting language running on a microcontroller, a good, easy to use, common scripting language. And Python was kind of the obvious choice. Um, and I had been playing with microcontrollers for a long time as part of my computer engineering degree, and part of sort of physics and experimental physics and things like that, and robotics that I just tinkered with in my spare time. So I had this sort of three ingredients of microcontrollers and scripting languages, and then Kickstarter was the platform um, to sort of bring it all together. Esperino, so JavaScript on microcontrollers, was sort of just had a Kickstarter,
Hmm.
and there were the other ones for various Arduino style breakout boards and other development environments, and there was just so many things going around, and I'm like, this seems like it's the right time to do something in this space. And my idea was to get Python running on a microcontroller. That was sort of the basic idea, and I think the thing I really wanted to go for was a zero tool chain, zero install. You didn't need to have anything, and you could
Hmm.
start working with a microcontroller. Because back then, when you got a microcontroller and you plugged in your computer, you needed to install, something to program it, um, and it was quite a lot of work to get something going. So the idea
Hmm.
with MicroPython is you plug it in, it appeared as a mass storage device over USB, um, and you could just copy a Python script to it, unplug it, and then it would just run. And so
Hmm.
you didn't have to have any compilers or really any knowledge about embedded programming in your Python script. If you knew Python, which is pretty simple language, to do basic things, you can turn an LED on, respond to a button, read an accelerometer, all in a few lines of Python, and you could just write it in an editor, whatever editor you like, Notepad or anything, and copy that file to your board, and it just ran. So that was the key goal, sort of, to make it so simple that it was just too easy to do embedded development. Um,
Hmm.
and then also in my mind at the time were things like, wow, Python is sort of known to be, well, not the fastest language. I mean, scripting languages are not powerful in terms of performance because they're interpreted. So I had the idea of inline assembler, and other accelerators to make things faster. So you could really blend Python with low-level assembler and bare metal routines. And so there's no RTOS in MicroPython. It's bare metal. And so you just really have the lowest access to the hardware that you can, toggling a GPIO, reading some sensors on an I2C bus. It's very, very low level and yet high level because the language that you write it in is Python. Um, so there was, all these ideas, and I tried to put them together, and I think it was quite successful. The Kickstarter was successful. We had a lot of people backing us. As I said, it was at a time when there were lots of Kickstarters going on and everything. It was very interesting melting pot of
Mm-hmm.
Kickstarter ideas and microcontrollers. And Kickstarter really did kickstart MicroPython in the sense that we got enough money to build 3,000 Pi boards, and that fulfilled most of the backers. I think there was over 2,000 boards we sent out as backers, and then to the backers, and then we had a bunch left over which we could sell, and then once we sold those, we could do another run, and we kept going from there. So
Mm-hmm.
without Kickstarter, it really wouldn't have been kickstarted. So it was quite a it worked as intended.
Yeah.
And since then, this was over 10 years ago, as you mentioned. Things have grown and steadily. More and more people have got on board with the idea of using a scripting language on a microcontroller.
Mm-hmm.
And I think one of the things that's driven that is the increase in complexity of microcontrollers and sensors and peripherals and all these things that you want to connect up and the products that you want to build. So, back 10 years ago, Wi-Fi on a microcontroller was not a big thing. Bluetooth was still pretty obscure. The sensors were pretty minimal. It was just a time of when you could start to get access to MEMS, like accelerometers and MEMS microphones and things like this. They were just starting up. And these days, fast forward to today, you have extremely complicated microcontrollers, various wireless connectivity, Wi-Fi, Bluetooth, different variants of Wi-Fi, the different technologies there, LoRa, Sigfox, so many different things that are so complicated, cellular as well, for example. And then sensors, as I was saying, MEMS sensors, accelerometers, microphones, temperature, humidity, gas, environmental sensors, actuators, and then of course relevant to OpenMV is vision, and then all the explosion in machine learning. And so the complexity of embedded systems has really rapidly increased in the past 10 years. And MicroPython has been there, gradually sort of adopting these technologies and exposing them to the user in easy to use ways.
Mm-hmm. It's actually, I think, the way you design this, it's actually like, when I think about the bare metal aspect of it, one thing that caught me when you were talking, when you mentioned the inline assembler, was just that you have total control over the system. Like if you don't do memory allocs, for example, the garbage collector, right, it doesn't run. And so truly you could write like a inline assembler loop or a Python loop that basically has 100% of the processor time, except for any interrupts happening in the back end. And if you didn't enable anything to have interrupts, you pretty much have total control over the system. And this is what I think, I think this feature is what really allows MicroPython to grow for a lot of folks, because it really doesn't have that huge performance trade-off that you would normally have with an interpreted system. Like you do have that ability to go low level when you need it to get the performance and capabilities you need, and then you can go back up high level for most things, right?
Yeah, exactly. I mean, you can do, post a JSON payload to some website, which, if you try and do that in C, it's doable, but pretty hard. But in Python, you can do it in a couple of lines, create your dictionary and then just do request.post. But then, as you say, on the other side, you can turn off interrupts and sit there in a loop polling a GPIO or bit banging a PWM or something. So yeah, you really do get that mix, that blend of extreme sort of high level programming and extreme low level programming in one go. So it's quite liberating actually using it, because you don't have the constraints of a PC in the sense of, you've got an operating system doing things behind the scenes. You've got full control over file systems and block devices and serial communications and intercepting network traffic if you like, and Bluetooth really low level or high level. So it's this mix of high and low level that is really interesting.
Yeah, and I was thinking about when you mentioned also that you can write the code in any notepad or etc. I remember a good friend, at least the microcontroller I started with when I first got into this stuff, was something called the Parallax propeller chip. Have you ever heard of it? Made by Parallax and Chip Gracie. And I had a good, I wrote a lot of drivers for the Parallax propeller before I started working on OpenMV. I did things like, I did the whole fat file system from scratch in Spin language, which was
Wow.
like Pascal, basically. And then I also did an SDIO driver in assembly. So like actually doing the, access to the SD card in assembly. Anyway, I did all kinds of drivers like audio output, VGA driving, screen buff, whatever. It doesn't, like, all kinds of stuff. And one of the cool things about that system that I thought was novel is something Chip Gracie mentioned about the concept of, he really wanted to build a computer that you could walk away from it 20 and then come back 20 years later and you could still edit the code. And it's crazy how you have actually brought his idea into existence with MicroPython. Because technically, yes, for any of these MicroPython based systems, if they are, if this was in the field running some code and 20 years later someone came back to it, you could still plug it in USB, and most likely there'd be some kind of USB port, given how long USB has maintained, that would allow it to function, and it would turn on, mount a file system, and you'd be able to see the code and edit it and fix, a bug if you wanted to, and then put it back into operation again. Versus any other system, it would be dead because, people would have long ago lost the compiler and tool chains and et cetera in order to like fix it, right?
True, very true, yeah.
So I think it's really cool that MicroPython has brought that that concept into existence. So I mean, okay, so that was 10 years ago. You launched MicroPython. Tell me about like what's, okay, lots of stuff has happened since then. Like, what are the highlights?
Yeah, well, lots of things. I mean, it's been a while. We've worked with Lego. I mean, MicroPython is in the latest Lego Mindstorms. Is the latest Lego Mindstorms operating system, basically. That's been really great working with them, with integrating MicroPython into the Mindstorms product, Spike Prime, and making it work really well there with Bluetooth and the peripherals. So that's been a pretty big highlight because I'm a big Lego fan, and so are all my kids. We have so much Lego. And we built a really cool Rubik's Cube solver out of Technic that runs MicroPython to solve Rubik's Cubes.
Yeah.
So
but you did the BBC microbit also, didn't you?
Yeah. So yeah, that's another one, microbit. With the back in when we were in Cambridge, so that all the getting out 1 million units to schools in the UK so that kids can learn to program and able to use MicroPython on the microbit to do that. And now microbit V2's been out and it's still going well. We're still working with them to make MicroPython work as well as it can. New things like audio, speech, and recording and playback. So there's that. Also worked quite a lot with the European Space Agency. So they wanted to integrate MicroPython as a scripting language for satellite control. So there was a lot of work done there initially to prove MicroPython can be deterministic and not need to use memory allocation dynamically, not need to use garbage collector, that it can run as in the opcode run again and again can run in the same amount of time, so it runs deterministically in terms of time and memory usage, and also do static code analysis to make sure the code's all as correct as it can be, run lots and lots of tests. So there was a lot of initial test coverage and sort of robustness improvements in MicroPython in sort of the earlier years because of all of the European Space Agency work, which was really fantastic.
Was there any like particularly hard challenge on making that robust? Like anything that needed to be majorly refactored?
I don't think so, in terms of not majorly refactored, because I did from the beginning have in my mind that it was obviously running on a microcontroller. It needed to be, deterministic and robust. And I think MicroPython has pretty good code quality. We have very good code coverage, lots and lots of tests, lots of CI. So it was more just going through painstakingly testing everything, writing coverage tests to get, you know, close to 100% coverage in the core code was a lot of work. Because the last 5% is, you know, always very hard. So I think that was probably the biggest thing, getting test coverage right up there. And then improving things so that memory did not need to be allocated in certain cases. So there was quite a bit of technical work in the virtual machine to fix things or change things so that they didn't allocate memory. So you can do a lot of stuff in MicroPython without allocating memory, which is important. So yeah, with that, so there was sort of the groundwork there, and then integrating MicroPython as a scripting language in the sort of space operating system that they have, and running on space hardware. So space hardware is like a Spark, a Leon chip with a Spark processor. So getting it working on Spark, lots of fun, because that's a, you know, another cool, interesting architecture that you don't usually get to play with. So doing that, and then making it so MicroPython could run sort of coroutine, well, as in within this space operating system, you like want to launch a script and run it to completion, or run it concurrently and run multiple scripts in parallel. So integrating it into the system there was another piece of work that we did, and it went up in the Euclid satellite eventually on a SpaceX rocket. MicroPython running on this Euclid satellite, which is a dark matter science mission. It's currently up there in space running. MicroPython doesn't run the entire satellite; it runs sort of bits of the scientific parts of it. But it's, yeah, that's very cool to know that exists. But yeah, so that's sort of some of the highlights. Other highlights: working with various clients, getting MicroPython running in their products. Like lots of medical devices have been built with MicroPython, which has been very cool. So like the actual medical device themselves, learning about how they work when I was part of the teams there was really interesting, and then making MicroPython work, which also it's good for me to sort of be, you know, on a team that's building a real product, because then I can feedback the experiences they have there to improve MicroPython then for everyone else. So a lot of the work that we do with clients is some of it obviously stays proprietary and hidden, but some of it then goes back to the community in improvements in the core for everyone, libraries, features, and then that's, you know, that's really fantastic. So there's that. Then there's also working with people who use MicroPython in education for teaching, as in like the microbit, but there are also other things working with them. So there's been a lot of stuff. There's been a lot of interest, lots of people coming along. Chip vendors being interested in MicroPython and wanting to support their chips, or, you know, helping us support their chips. And then recently, something totally unexpected with PyScript, which is running MicroPython in the browser, compiled to WebAssembly.
Oh, so, I heard about this. I think.
Yeah. It's, I mean, MicroPython's found a sort of another home there, because it's a minimal Python interpreter, and in the browser, you want your page to load quickly. So MicroPython's only like a few hundred kilobytes of an asset to download as a web asset, which is, you know, less than an image almost. You know, it depends how big the image is, but you'd barely notice it, and suddenly you've got a Python enabled sort of development environment in the browser. So you can write a web page in Python now using PyScript. MicroPython is sort of the Python engine within PyScript. You can also use CPython if you need more complexity, but MicroPython's good because it's very quick. So that's sort of another whole entire sort of area that we can concentrate on. So yeah, the things just keep coming, the uses for MicroPython in various ways. But what still excites me is the sort of fusion of hardware and software. Is that I wouldn't enjoy just working on the software side and also just working on hardware. You know, I also like the software. So putting them together, building boards, building hardware, building products, wiring things together, and then on the other side, using MicroPython to program them and make them work. This fusion is, I think, what makes it successful, is that you're kept real, you're kept grounded by having hardware to actually run on.
Yeah.
and constraints within the hardware. Like you have a limited amount of RAM processing. The constraints make things interesting, as in everything in life.
Yeah.
So that's, I think this fusion of hardware and software is very important for us to keep sight of, keep hold of, make sure we have that, so that MicroPython has a direction to go in.
Yeah, no, I definitely think that's the case. It's you know, for the systems that we've been building together and such, it's always like, having these constraints helps define how you think about things, and it's actually cool because you have trade-off conversations about one way to do something or the other, and then really discovering elegant solutions for problems, and then seeing how those elegant solutions actually lead to more novel ideas. Kind of creating inventions. That's what's cool.
Yeah.
Mm-hmm. So, what I wanted to introduce today, and, this is a project that, you've been working on with us, OpenMV, for a while now. And just to give some background about OpenMV to our audience, we've been working with MicroPython now since 2015?
Yeah, a long time.
Pretty much since MicroPython began, my co-founder Ibrahim has been committing, fixes to it. Like the original, PyDFU, for example, to load boards is Ibrahim's creation. And so we've been around since the beginning working with MicroPython, helping drive things forwards. And, we actually do care about the contributions and how we commit back to MicroPython and build it up and staying in sync too. We're not just kind of a fly-by-wire organization that's taking the code and making a fork and then never putting anything back. We actually want to grow the community and make sure people have robust systems and such. Anyway, so what I wanted to introduce is we've worked with Damien and we've built this new thing called the OpenMV Cam AE3, which is based on the Aleph Ensemble MCU, and it is now running MicroPython. And this is a very interesting new CPU that I think Damien would agree this is what keeps things interesting, on where we're seeing ridiculous gains in hardware for microcontrollers. If we look back to the Cortex M4 that you started on, well, actually, what was the first MCU that you started programming with, Damien?
Yeah, the Cortex M4. Yep.
The M4 was the first one. Okay, yeah. And if you look back to the M4 and the M55, like what strikes you as different between these two types of processors? Like, what are the major highlights?
Well, actually, it's more about the similarities, really. I mean, it's still Thumb 2.
Yeah.
The architecture is still the compiler's the same.
Mm-hmm.
The architecture is similar. The way the interrupts work is still a Cortex M. Yeah, have gone. I mean, the M4 and then the M7. The M33s, the M55s, introduce security, secure and non-secure areas. So, yeah, you can have areas of the microcontroller that are off limits to other parts of the code.
Yeah.
So that's the main thing that's been introduced. But under the hood, also, there's lots of other like performance improvements, pipelining, and the architecture internally of the microcontroller and the buses and the way things all interconnect. So you get for the same clock speed, you get more performance, and also less power consumption. So it's sort of been a refinement from ARM's side of just better core CPUs. And yeah, they're good, but I think the users wouldn't notice so much of a change except performance, in terms of actually going up in the CPU. But the thing that you notice though is the peripherals, the different peripherals. Yeah. And then in this new Aleph Ensemble series, you have multi-core, a bunch of chips, and also the Ethos machine learning accelerator. So these are the things that I think, as a sort of builder of product, of using these things to build stuff, you would notice performance, lower power, and all these new peripherals that come out.
Yeah, but I think the biggest thing though is the RAM on board. Actually, that is what strikes me as really. I mean, yes. So with these new Cortex M55 processors, We've actually got two. One of them is based on the so we've ported MicroPython with the help of Damien to the the STM32 N6, which was just announced, and so we have the OpenMV Cam N6, which will be that we've launched, and I don't have it as a camera module here, but let me stick one on. So there you go. It's a FLIR boson, very expensive thermal sensor that we support for really fun thermal vision stuff. But no, you have the M55 processor core now that we're running MicroPython on, and so that offers. I mean, we're using the vector instruction stuff. MicroPython is not yet using that, but I think if you guys switch to LVMM, ARM actually recently, it's LLVM, right?
Yeah, LLVM. Yeah.
Yeah. If you switch to LLVM, ARM actually made that available for free to use, so you can just like download it via CI. And on the M55, actually, the compiler is smart enough to properly pipeline and also auto-vectorize places in your code. So you may wish to, once we get these boards out there and people are able to play with them more, it'll be interesting to see if you retarget on LLVM what the performance difference looks like, because we noticed that even in hand-coded stuff where we wrote individual assembly instructions to do specific operations, and pretty much everything was in assembly. Well, like intrinsics, so not assembly, but we're writing the intrinsics to do register operations, and we're controlling things very carefully. We still noticed a 20% speed up just in our hand-coded code, just from the compiler being better and optimizing the time slices of where to put instructions. But then it also will just auto-vectorize stuff for you. So it might actually like speed up the core routines in MicroPython just automatically without having to do anything, as long as the loops are easy for it to understand, et cetera. But I think like the bigger interesting thing is just looking at, we're seeing with the Aleph Ensemble, for example, we have microcontrollers now that have 13 megabytes of RAM on chip. And so it's really like, this is where I think, this is where Python really starts to shine, because it's like, you had your heap on the Cortex M4, right? But you could still run out of memory, basically.
Yeah,
but I mean, tell me what you could do with a 4, 5, 6 megabyte heap now.
Yeah, no, you're right. The having all this extra RAM, yeah, it's really interesting on the onboard RAM. Of course, you can add external RAM, but it's not as fast or deterministic. Or it's also extra power and extra space on the board. So internal for 13 megabytes RAM. And also, the flash is like 4 or 5 megabytes on these things as well.
Yeah.
So the RAM, and also they have really interesting power architecture, like many power domains, so you can turn things on and off selectively and only use the bits of the chip that you want. So, and the RAM is divided into lots of sections, and you can turn the bits off you don't want. And so there is lots of internal complexity, but also great features. And the RAM these days, if you have a display and you just need like a megabyte of RAM for the display buffer, that's super important to have. Just if you have 10 megabytes available in your heap, you can use 1 megabyte for a frame buffer, or a double frame buffer even. And then with SSL connections, they are notoriously big and take up lots of RAM as well. So if you have a couple of SSL connections, there goes some more RAM. So with the complexity of the things that we have, the RAM is definitely necessary. And in MicroPython, we have this feature now where the heap can grow automatically as you need more RAM. So I mean, you start with a small heap, which is sort of faster, and then if you need more, it can expand. So we've got the capabilities to have all this.
Oh, is that a new feature? Is that like S-break, like how they do it?
Yeah, it's auto GC heap adding. It's quite a recent feature. It's very useful. But with as we probably will talk about, the machine learning models as well, they obviously need quite a bit of RAM for their neural network, all the weights, the inputs, the outputs, doing speech, audio processing. You need quite a bit of RAM input output buffering, and vision as well. So having internal SRAM easily available in sort of large quantities, you don't have to worry about so much anymore. Python, using UpRAM, because before you had to be a little bit careful and then run garbage collection. If you only had like a 50K heap and you wanted to do something mildly complex, you have to be careful. But these days, with megabytes of heap, Python becomes less of it's just a great tool now to solve the problem.
Yeah.
The thing that dominates memory usages, as we were talking about, is frame buffers and audio buffers and vision and matrices, machine learning. So you can start to solve real problems, and Python is no longer in the way. It's just there to help you.
Yeah, I think about that just because I remember, like, in my Parallax propeller days of 32 kilobytes, which was your whole program and data at the same time. Everything had to fit in 32 kilobytes. And I remember how, like, I would focus on optimizing things down to save a single byte. Because if you kept trying to save a byte here and there on every single thing you did, you would save like an extra 500 bytes, and then that would equal a kilobyte, which was like, a huge percentage of your memory.
Indeed.
But it's interesting to think about now because, as I imagine more complex systems and we're starting to do things that are higher level, it really approaches more like a computer system, like really pulling off what you would use embedded Linux for, really, at this point. Like, as you mentioned, like a web server, right? You could technically, if you have this much onboard RAM, there's no reason why you can't have a whole bunch of sockets open with multiple connections, and you streaming data to multiple people at the same time, and that could be powered by MicroPython. Like the fundamental limit there is just, you would run out of memory, and so you would design things to be memory efficient. But if you have plenty of memory, then why not be able to support multiple connections opening up? That kind of brings up, like, what could you do if you sync AIO, the async IO library, and how to make web servers. It also brings in, like, when you're doing web requests now, like, you can just do a file transfer upload, like a multi-part file upload, for example, chop up like large files into segments, and you're just pushing that online. And you're no longer worried about, running out of memory during that particular transaction, or trying to constantly clean the heap up. So it's I don't know. I just find it interesting because it's like, would you say not like one of the biggest pushbacks you get from people with MicroPython is they're always concerned about the heap, right? And just like things being non-deterministic and running out of memory when you're playing at a high level, right?
Yeah, I mean, I think you'd be surprised. It's not that much of an issue. People do worry about it. They sprinkle gc.collect here and there, but the actual severe fragmentation is not. It's not really a practical problem. In the end, there are always cases you can find where things don't work, but I mean, yeah, people coming to it are wary because it's like a dynamic language and it does allocate memory, but we go to great lengths to make it work really well and to not use memory where possible. And even though we have a lot of memory and a lot of processing power these days, MicroPython is still heavily optimized to not use memory and to be small and to be efficient. So it sort of works better and better now because the processors are more and more capable.
Yeah. What I think one thing to hit on, though, that we're excited about with the new OpenMV cams actually is there was a library called ULab that was actually ported to MicroPython, well, NumPy basically. Voltron Zaltros, mispronouncing his name there most likely, but he got basically like a version of NumPy running on board MicroPython. It's not everything, but it's becoming more and more complete. And it really starts to change how you think about MCUs and how you think about processing of data sets, because it has stuff like FFT, inverse FFT. You've got every single math operation you want to do. You have argmax, argmin, mean, standard deviation, all the basic processing features to do things with arrays. And it's starting to include a lot of the SciPy functionality and also linear algebra. capabilities, like it can do matrix inversion. I remember like just running that once. I needed it to like invert a matrix, and it totally did that for me. And that's like a very, if you've ever done Newton's method, was it not Newton, Gauss's method?
Well, row reduction by hand.
Yeah, that was fun in class, but
Yeah.
but being able to do that on board, I was just doing the 3x3 matrix, but you think about that now coupled with megabytes of RAM, and all of a sudden you're talking, yeah, I can process like 100+ kilobyte matrix or something. And what's interesting about this is it gets into where I think a lot of the future lies with why we're glad to be supporting MicroPython as the platform of choice for OpenMV, and where I think things are going for microcontrollers. And that is that you got to think about data, right? We're going to be dealing in the future, as you mentioned, with all these sensors that are coming out. You're really going to want to process these sensors, and it can be time series data, it can be 2D data, maybe it's even 3D, but everything's going to come down to basically fast number crunching, the ability to take in large data sets, large amounts of data, and then efficiently process that, but do it at a high enough level where you're able to actually get work done. Because I think if you're programming in C, if you're just like writing for loops or triple nested for loops, or in the case, like if you're doing a convolution, for example, on an image, that's a quad for loop just by default. And so when you're programming at that level, you're not getting work done, versus when you use something like vector operations from NumPy. This is a library that allows you to slice matrices and basically with a single line of code invoke a call that could sum every column in a huge array up, and and then find the median, or find the average or argmax of all those columns, for example. You can do some really fun stuff. In particular, for the OpenMV Cam, we're actually using NumPy. We have ML models, and I actually want to demonstrate that in a bit. Running on board the OpenMV Cam AE3. So this is the guy, super tiny, 1 inch by 1 inch, and we're actually all of our model post processing in MicroPython. And this is really what blew my mind, because at first I was not for originally doing all of the post processing using NumPy and MicroPython and allocating a 100 kilobyte matrix on the heap. I thought that would be slow. And it turns out actually it's not. And you can actually do all of your math operations to post-process a YOLO model, for example, all in MicroPython using NumPy, using ULab basically, and keeping everything at a high level. It allows you to like program a microcontroller. Like imagine a data science team who's figuring out how to process models using IPython notebooks, for example. It means now, like with MicroPython, you can basically have similar code that they would write in the cloud running on board a microcontroller, which is really the mind. That's the mind explosion thing, when you realize that like the code that's in the browser could be also running on the hardware that's the target device. That there's no translation layer where you're having to throw over the fence. Okay, the data science team that's trying to build a product said this, and they throw it over the fence, and now the embedded engineers have to figure out how to take Python code and rewrite it all to be C, right?
Indeed. Yeah, and I think the rapid development is another big thing. Like the fact that you've written this, processing pipeline in Python, it's just very easy to change a few parameters or add a new bit of the pipeline or whatever. So the rapid development is also what makes it very interesting, that by using Python, you can quickly iterate on your idea and your design and make things work and explore.
Yeah, no, definitely. I think so also. It's and one last thing to this point, which is, when we bring across these like the Cortex M55 now that we're unlocking vector instructions, which is like, back when you started on the M4, did you ever think vector instructions would be a thing that's coming to microcontrollers to you?
Yeah, maybe.
But
no, they're definitely no, very cool. They didn't have them back then.
Yeah, no, by the way, for the audience, vector instructions, what these mean are something called SIMD, single instruction multiple data. It's where we can say we take we might have an address, and we might say, okay, load up these 16 bytes, and then those will be flown into a register, and then we can say multiply all 16 bytes by like a number, and so we get 16 multiplies in the same clock cycle versus one, and then you can kind of keep that operation going in parallel where you're doing like 8 or 16 things at the same time, so you get huge speed ups. And because all of that can be, you could have all of that code hand coded in MicroPython in C, and then the Python level is just able to use it, and it's already proven, so you're not having to rewrite that over and over again. Like for the ULab library, that could be accelerated using vector instructions, and then everyone would have the benefit of using the vector instructions without having to write vector instruction code.
Indeed, yeah. I mean, that's the benefit of a high-level language, is that you get to leverage well-proven low-level routines in a composable way. Yeah,
that's one of the benefits. Okay, so do you mind if I show off, Damien, like what you can do with these new systems? I just wanted to give people.
They're very cool. It's a very cool piece of hardware, this OpenMV AE3 board.
All right, so check it out. Let me just hook this guy up real quick right now. Okay. So we've got the camera hooked up, and let me just launch the tools. And of course, it's a live demo, so let's see how this goes. Is it a disaster? Is it success? Who knows? Only time will tell. Okay. And one other thing, I wanted to show you guys also just something that's going on in the back end, just to, I think it's, I try to show this to everybody now that we've done it with getting ULab working, just because it's so powerful with this, really what MicroPython brings to microcontrollers, and just the way of thinking about things now. It definitely was something that really blew my mind, and I think I just want to share it with more people, I think, which is important. So we will open this up also. Okay, cool. Wait, just give me a sec. Almost there. Computer's laggy. All right. Okay, great. So let's share. Okay, so we're switching over to OpenMV IDE, and it's coming through now. All right, great. And so what we've got is the OpenMV Cam AE3 running, and it's seeing me right there. And I'm just going to take a step away a little bit, because it's tuned to look for a person. So if we just walk in the back here, we can see that it is detecting a bounding box around me, and that is the YOLO V5 algorithm running. It looks like there was some lag there, and it crashed. No good. Let's try that again.
So you've got the code there that it's actually running. Take a snapshot, predict from the model, and then go through all the boxes. Yep.
And so it's finding my mic there as a person. Okay, there we go. Now it's running. So we've got a basic model here. This was hastily trained for CES, so please forgive it. You can do better when you make your own. And it also wants to, I also need to be closer to it. So that's the trick there. But big important thing is that it's running on board, and it's able to kind of see me and detect a little bit. I think if I lower the detection threshold, it'll do a better job, but I really just need to stand farther away. But anyway, you can kind of see it working there, and that's really the live demo that I wanted to show.
And so you're streaming the video from that OpenMV board back to your PC.
Yes, we're streaming the video.
Yeah, but the code that you see there is running on the actual board.
Yes, the code that we see there is running on the actual board. It's not Yeah, so that's all it's running on board. So there's actually a few different pieces of technology that were going on here. So by the way, the glitchingness of it freezing there, that's an issue with my laptop. There are some fun bugs that we got to work around with the USB drivers on Windows. So every time you see that happen, it's because the Windows kernel threw away half the data that was coming through the USB port, and so we're recovering from that error. Hopefully, we'll get these issues worked out as we get everything more mature. Just one of those fun things that only happens on Windows, not on other PCs, though.
So it's doing detection there at about 20 FPS.
Yeah, it actually goes a lot faster. So if I disable the IDE frame buffer, which is a load, it's actually doing 28 FPS. And so this is this little board actually is drawing 60 milliamperes of power, and we're running YOLO v5, which is a neural network at about 30 FPS, so 28 FPS for 60 milliamperes. Just to put some comparison on this, the OpenMV Cam H7, which is our previous model with just the Cortex M7 processor, that would only go at about 0.3 frames a second, and it would draw 180 milliamperes or so.
Yeah, amazing.
So if you can,
so you're doing the YOLO on the ethos here.
Yeah, the ethos. Yeah. So if you were to do the numbers, by the way, let's say 28 FPS versus 0.3, that's about a 98, basically 93% speed up. Sorry, 93x speed up. Yeah. And then the power consumption wise, 180 versus 60 is 3. So we got 93 times 3. So we're about 280 times faster.
Yeah.
If you think about that.
This is because of the ARM ethos, U55. So it's a dedicated piece of silicon in the microcontroller that's doing the matrix multiplication as quick as it can.
Yeah.
So yeah, I mean, as you say, previously you could still do the algorithm. It's just slower and much less power efficient because you've got to do those multiplications and additions and matrix operations just manually in the CPU. But now the machine learning coprocessor is doing these matrix operations for you very, very efficiently. So yeah, that's the key. That's the key thing that's going on here.
Yeah, and there's a few pieces of technology that make this possible. The first one is you've been working on a new feature called ROMFS, right? Do you want to talk about that a little bit?
Yeah. ROMFS? It's it's a file system which is read-only and memory mapped. So you mount the file system, and in the file system is a fixed set of assets and code that you have previously put on the device. And this, it looks like a normal file system, and you can load files, but you don't actually have to load them into RAM. They stay in ROM, and you can read them, the data from ROM, and operate them on them in ROM. So in this case, you've got your, I guess, your weights for your model stored in ROM. From Python, it just looks like a normal file, and you can just use it like a normal file. I mean, obviously you can't write to it, but that's really great. So you can change a model, but it doesn't take up any RAM.
Yeah, no, and that's what this is actually super important for us, because all of these MLA accelerators, they do not, they totally need memory alignment. So it 100% will instantly crash if it's not like 16 or 32 byte lines, which matches the cache sizes and cache lines and et cetera, lots of lower level memory architecture issues. And so ROMFS, it provides a way to basically, flash the model into external flash, right? Where we can load it off of an OctoSpy memory. And so OctoSpy offers something on the order for the OpenMV Cam AE3, it offers 200 megabytes a second read speed. And for the OpenMV Cam N6, it actually offers 400 megabytes a second read speed. So those are some, if you think about it, those are some numbers you're putting up there. I mean, that's like high-end memory performance. And we're able to store the model itself basically in that, and then you can just execute it in place. And so this allows you to kind of like have a separate flash chip that is hanging off board the device, and that can have, pretty much as long as you're willing to pay, because the more expensive ones are more money, you can have, up to 512 megabytes of stuff, which could be models and other various things. For the OpenMV Cam AE3 and the N6, we're going to be doing it only at 32, just because that's where the cost versus size starts to make sense. Going above that starts to get really expensive. But yeah, no, it's a super huge feature. It's very important because it really allows you to have a sane way to manage linear offset, to manage how do you say
alignment.
Yeah, alignment, but also it's a sane way for you to manage statically defined assets. Like, they don't have to be built into the firmware image anymore.
Yeah.
Previously, they would have to be built into the firmware image, basically.
Yeah. No, it's very cool. I mean, this highlights just all of the sort of one aspect of all the technical details that are underlying this technology here. Like, there's a lot of stuff going on, but there's only 37 lines of Python code, half of it's comments and imports, but like most of what's going on here, there's a lot of stuff behind the scenes to actually do that model predict. And yeah, it's really great.
Well,
it's so easy to use.
Yeah, this is what I wanted to talk about, actually, which is, well, I can go over what happens here for the audience, which is going to be cool. So what we're doing actually is, so we have a whole camera frame buffer driver that's running inside of OpenMV. So we actually do something called triple buffering. So when we're in VGA, we actually allocate multiple VGA buffers. There's 3 of them. And so there's an interrupt-driven driver that's basically writing to 2 back buffers. And then your code just grabs a front buffer. Basically, whichever buffer is free and available, we grab that, you execute on it, and you're pulling that data and doing something with it. And so that's kind of how that's going. And then once you get that image, what we do is we actually, when you call this predict function, we're actually doing some Python magic to take so it's taking a list of objects that matches the tensor input. So a model basically accepts a list of tensors, a list of when tensors can be multi-dimensional arrays, right? And we are taking that list, which is equal to the number of tensor inputs the model takes, and we're transforming that into, for an image, for example, that needs to be transformed into a RGB channel output. So it's going to be width and height, and then 3 channels, which are RGB. Those are 8 bytes. Those are 8 bits each. So we're transforming a RGB 565 image, which is 16 bits per pixel. 5 bits red, 6 bits green, 5 bits blue. We're turning that into RGB 888, which is what the model has. And so we do that in the background as fast as possible. We also take care of things like image scaling and cropping and all these other fun stuff to kind of get you to take, a non-ideal image that's like bigger than the input size. This model takes in a 224 by 224 image array. So we have to scale that, we have to crop and scale that VGA image down to 224 by 224. Anyway, in the back end, that goes to the model, and then that gets passed to the Ethos U55 accelerator. That runs through it, runs the model, uses the weights here and everything, and then it returns a massive Python array of floating point values, which represent the output of the model. And so that's the thing I wanted to touch on with ULab and MicroPython. So we've got some code linting built into OpenMV IDE, so it's going to complain about all of this. Let me see if I can turn that off for folks so we can read this.
So this is the callback. This is the callback you're passing to your underlying process.
Yeah. Yeah, it's the callback we're passing. So what I want the audience to take a note on is that is it to post-process a YOLO v5 model. There's something called the non-max suppression class here. This is actually quite complicated inside, but it's also written in Python, pure Python. But basically what we're able to do with NumPy, this is the core of the YOLO v5 post-processing. So the way to think about YOLO v5 is that you're going to get an array that has, it's a 2D array really. It's each row in the array is about 6 values. You have X, Y, width, height, a score, and then a variable size list that is the number of classes that are in that bounding box position. And so this is variable size. So this could be 1 to n numbers, and then that is a row. And then you have, some number of rows. And so typically YOLO outputs like 6,500 rows. So this number right here, if we were to say how many rows are in it, it's like 6,500. It's actually quite a large array. It's like 6,500 times 7 floating point values. So it's in the couple, this is a couple thousand kilobyte structure actually that we're playing with. And this is where having those megabytes of RAM comes into play, which is you can just allocate that and process that. And you don't have to like try to deal with running out of memory or anything like that. The most important thing you're doing with MicroPython is you are grabbing that array and you need to threshold it to figure out what are the non-zero columns. And so what's going on here is we're just grabbing all the indexes, like what this does in NumPy is it says select every single select all the columns of score from every row, and then threshold it by a threshold. So find me the non-zeros, right? And then once I do that, it'll proceed to grab all of those. There's some stuff I have to do to fix up there being a tuple there. Check to see did it actually find nothing or did it find something, and then I take every single one of those and make a new ND array, which is just the ones that pass, right? So just imagine for a sec what that would look like when you write that in C, Damien.
Wow. Yeah, I mean, yeah. I like writing in C. MicroPython's written in C, but yeah, I don't want to write this kind of stuff in C. Yeah.
Yeah, it's not a conceptually hard thing, but I mean, if you wanted to work quickly and try to like maintain, what you could do and build out ideas and thoughts, that would take you a lot longer. That's like a double, triple nested loop with some other. Remember, this copying between two values. There's memory allocation here, lots of stuff. But once you just have the passing values, then it's easy to do stuff like get all of the scores of the passing values. You can also do something like this. This is a really fun instruction here. This is saying grab all of these for every row of passing values. Grab columns starting at where the class list starts. That's a variable size. Grab to the end of it, and then find the argmax of that value for every row, and return to me a new vector that gives me the highest class value for every single row. Now, this is actually an extremely complicated loop that you'd have to write, and it's one line of code. And then finally, you can do stuff like extract the XYs, extract the bounding box sizes, and shrink them by half. And then you can build your Xmin, Xmax, Ymin, Ymax, and it's all just a bunch of linear operations like this. So the thing though is that like this normally by writing it this way, everything's vectorized. Like everything underneath the hood is executed in C, but anything that is not under the hood, for example, it's all just like single line statements though otherwise, which is what makes it really cool.
And so this is computing that blue bounding box we see around you.
Yes, yeah, but it technically could be it's only doing like one bounding box at a time. Well, if I take out the non-max suppression, it's actually a whole number of bounding boxes. I can't really show that running on it because this code is not part of the application image, but it's it is it's computing that bounding box, but it could be doing hundreds of them at the same time, and it would be the exact same code.
Yep, and all this is running at what 28 or currently 1920, but up to 28 frames per second with minimal power consumption.
Yeah, with 60 milliamps of power consumption, and we haven't even really started optimizing everything here. There's a lot of fruit left to pick on making the performance go up. Right now, actually, the ML processor isn't the slowest thing. The slowest thing is actually the CPU because we haven't vectorized everything yet. So there's still a lot of work to do, but it's just the initial. Where we are on this product, it's already 200, as I said, 280 times faster than.
Well, that brings it above a threshold where it's kind of like usable sort of thing, as in 0.3 frames per second is, well, you can do it, but when it's real time.
Yeah. But this is where I think this is what has really jazzed about the future of MicroPython, it's like what I just showed you is the worst it's ever going to be, right? Like this, we only have we're only, this is the worst it's ever going to be. Just like they say in AI stuff, it's like when you see the Sora video generator, having people exploding out of people and such, and it's not being able to do a good job, but it's still like looking photorealistic-ish. You're like, that's the worst it's ever going to be. It's going to get a lot better as we continue to pour resources in this.
But it's already very good. I mean, you don't have to. It's already amazing what's going on compared to 10 years ago. This was not feasible.
Yeah. And it's really what I think excites me about MicroPython is that as you saw right here, we were doing YOLO, running on board a microcontroller, and we are post-processing the data in Python. We're actively, and the Python is not being used as a secondary thing or a hamstring or something that, it is the main show, right? It is the main code path for the application.
Yeah, it's very cool.
Yeah. Anyway, I think we should kind of wrap it up in a little bit here. So before we go, I just wanted to talk to you about the future, Damien. Like, what are you thinking about MicroPython after seeing this? And, where do you think things are going to go now from here? What can you imagine for the next couple of years?
Yeah. Wow. I mean, the complexity of microcontrollers and peripherals and, connectivity, I mean, it is exponentially increasing in the sense that it's just getting more and more. And every time a new microcontroller comes out, it's another 10,000 pages of data sheet that you have to read and understand. A long time ago, it was a few tens of pages, if not 100, but now it's an order of magnitude more. And so it's hard to keep on top of things, but it's fun. It's exciting because there's so much interesting technology. And I think this is what we're seeing with like this Aleph Ensemble and the STM32 N6 is it really is just the beginning, because these are the first chips that have this fusion of application CPU or MCU microcontroller and alongside ML machine learning accelerators, and they're only going to get better, as you say. Things are going to get better from here, so there's going to be more of this. And it's going to be more, I guess, our job, you and me, is to make these things more accessible to people so that they can write a handful of lines of Python and do something really amazing like image detection and so on, and audio detection. So I think, yeah, we've got all these new things coming up which we can use and have to work out ways to make them easy to use. So there's a lot of stuff. There's a lot of work to do, but it's really fun. As I said, though, connectivity, all the different kinds of wireless, like I know on your board you've got Wi-Fi and Bluetooth for connectivity. So you just plug a battery into this thing and set it going, connects to the internet, and can do whatever you want it to do. So like, yeah, the sorts of things you can build these days is sort of almost limitless. It's and it's just going to get better. So, I mean, with MicroPython, we've got to keep up with these things. MicroPython core is pretty solid. It doesn't change too much these days because it's pretty well battle tested. So the things that we concentrate on are supporting new chips, new ports, new sensors and things, and adding features like ROM-FS. So we're looking forward to MicroPython 2.0. We're still at sort of MicroPython 1, 0.25 is coming out so very soon, or may even be out now. And we're looking forward to MicroPython 2.0, where we'll try and clean up a few inconsistencies, remove some legacy things from 10 years ago, and I think improve the user experience with developing in MicroPython, a big professional application where you've got lots of libraries, Python libraries that you're depending on lots of resources, like you've seen with YOLO models or other machine learning models. So that's what we're working towards, is making it, taking it from 10 years ago. The original goal was you just write a single script flash an LED and read a sensor. But today you've got these big applications and you've got all this stuff to do, and you've got libraries like ULab which give you amazing capabilities. And when we'd love to be able to make ULab a pluggable component, for example, so you could just install ULab instead of having it to build it into the firmware, and LVGL, sort of a graphics driver, so you could just install that. So C level drivers could be written and made pluggable, just like Python is pluggable. So these are the sorts of things we're thinking about, and very much looking forward to. But as I said before, it's the driver is the hardware. Like, without the hardware and without constraints and these new things that are coming up that we have to support, without that, we don't have much of a direction. I mean, we could, do other things, but it's great to be driven by the acceleration and in all of this microcontroller and IoT and machine learning technology that's coming up, and be driven by that. Need to support it, want to support it, and make things work really well. So that's sort of the ride we're on, and it's very, very exciting.
Yeah, no, and just to second that, before we go, yeah, it's my thought on this is that when you combine these new AI microcontrollers, which have amazing capabilities of RAM, really high-end processor resources, and AI ML, this is really where MicroPython starts to not just shine, but become like the clear choice forward. Because, what I just showed you, you really wouldn't want to write that in C. Like, you really don't. And that's just one model, by the way. There's a lot of ML models that have more interesting post-processing layers. And so, this is where MicroPython really starts to become a clear choice for how to do things in the future, on how we can actually take this, bare metal and these really powerful CPUs, but bring them to the people in a way that is easy to use.
Yes, indeed. And then you can easily just add a web server to it.
Yep.
Like asyncio. Create task web server, and you're done.
Yeah. And before I go, one thing we forgot to hit on throughout this whole talk, but I think our interview is getting too long now, is we actually have some really cool features on the Aleph Ensemble. It actually is a dual core CPU. And so you can actually share code between multiple cores on board it using MicroPython, and actually have two separate threads running using the UASync.io library. More on that later. Maybe we'll do another interview, maybe not. But yeah, there's a lot of fun stuff coming out with MicroPython and what you can do.
Yes. With multi-core, sharing code between cores. Because with the Aleph, there's this high performance and high efficiency Cortex M CPUs. So the high performance one is the one that's running MicroPython usually, and the high efficiency is sort of in the background, and you can send MicroPython code to it and get it to run on there, and do things independently. So yeah, we're seeing a lot of multi-core chips these days, and the Aleph is many multi-core with the ethoses as well. So yeah, it's lots of interesting, as I said, it's just another example of the cool technology that we make to make MicroPython, make it easy to use. Yeah, one of the things that's coming out. Anyway, thank you all for watching, and also please back the OpenMV Kickstarter. Indeed, yeah, it's a cool board. Cool. Yeah.
All right. Thank you, Damien, for joining me today and talking with me.
Kwabena, thank you. It's been great.